When we talk about connections and connection control, we need to separate out connectionless data transfer from connection-oriented data transfer. Remember, each protocol data unit is treated independently and connectionless. HTTP is connectionless. So each individual protocol data unit, at that point it's called data, is treated by itself as a whole. And so the authentication needs to be inside of there in some way, shape, or form. When we look down the layers and we go to IP, the authentication needs to be within that particular packet before we de-encapsulate. And in IP, it's not. In connection-oriented data transfer, we create this virtual circuit, and to disturb that virtual circuit, we need to predict where the conversation is going. That's what we do when we do hijacking at the TCP layer. We look at the session variables and pass that data back and forth and get inside of that passing back and forth as those variables increment. That's your sequence number. If we can predict that sequence number in a connection-oriented data transfer, we can take over. We want connection-oriented from a security standpoint. We also want it for lengthy data exchanges. Connectionless requires that somewhere up above this level that we have authentication, or that each individual protocol data unit is in fact authenticated. And that's very difficult to do without a lot of overhead and a lot of management. Okay, so now let's talk connection control. If the protocol details must be worked out dynamically, okay, fine, we can agree with that connection control. There's a logical association or a connection established between the two entities. If we can break the logic in that, again, we can take control. So let's talk about the phases of occurrence. So connection establishment, data transfer, connection termination. Connection establishment, SYN, SYNAC, ACK. Data transfers, bunches of SYNs and ACKs going back and forth, the sequence numbers incrementing. At the very end, FIN, ACK, FIN, ACK. There, we're done. And that's the example from TCP. It can be interrupted and we can restart that. And there is a recovery phase where we can handle errors. Suppose along the way that one of the hosts on either end gets busy. Instead of doing the acknowledgement of the next packet and saying, okay, give me 1,000 more, it can say, give me 500 more because I'm kind of busy. Give me 250 more because I'm busier. Give me 1 more because I'm really, really busy. Give me 0 more and wait because I'm really, really busy. So here's your phases of your connection-oriented. Connection request, connection accepted. Okay, that's that SYNAC. Data exchange and the acknowledgments as we go along, multiple exchanges, and then the termination of it. Let's look at connection establishment. So each entity agrees to exchange the data. They've got the underlying communication, and now we're up in the TCP layer. One station issues the connection request. That's usually the client side of things saying, hey, I'd like to talk to you. And then the receiving entity says, I'll accept this request whatsoever. Most of the time, servers automatically accept. There could be a negotiation in there, especially when we're going to an upper layer protocol like an SSL protocol. We'll negotiate some other variables. It may be, okay, this is our speed, this is our data, this is our encryption algorithm, this is how we do that. We'll do some sort of syntax, semantics, and timing, getting us ready to go. Now the rule is that both entities have to use the same protocol. So if there's a difference in the versions of the protocol, we need to have backward compatibility. The perfect example of this is when we're talking about SSL connections and TLS connections. TLS is the newer version of the protocol, and if in our negotiations we go back and forth and you say, well, I only speak SSL version 1 and you speak TLS version 2, can you go slower? And we negotiate down. So sometimes what we can do is we can prey upon the fact that you will be backward compatible, or I will be backward compatible. Where this doesn't work is in instances where we're using something like IPsec. IPsec with the simplex connection says, no, if you can't communicate with this level of encryption and this level of rekeying, no, not at all. Now you're going to have options and features in there also, but usually this backward compatibility thing is the thing that we prey upon. Remember, we also agree upon the maximum size of the protocol data unit, how much data we're going to transfer. And some stations will restrict to lower octets. Data transfer and termination. So we both agreed on the data and the control information to exchange back and forth. We get that out of the way. We do the data flow and acknowledgments. We can do the acknowledgments in both directions. With TCP, that's exactly what we do. Some, like UDP protocol, since there's no connection set up, we just keep on sending and praying that we'll actually get the response. One side can terminate the request. It doesn't have to be both sides. It can say, I want to do a reset. That's why when you're attacking a network, an intrusion detection system can come in and say, we're going to do a reset on that channel on both sides. They're sending one reset one way and one reset the other way. It's not, they're sending them to each of the stations on either end. So at the termination request, we can also step in and start working against our adversary.